So today's lesson is based on molecular polarity, and we've already talked about bond polarity, and we've already talked about shapes of molecules. So we're going to talk a little bit about how we can identify whether or not a molecule is polar or nonpolar. We know that when a molecule has a separation of charge, there is one end that ends up being positive and the other end is negative, and so the molecule will end up becoming polar. What that means is that these are little water molecules here, and these little water molecules have a positive and sort of negative side, even though they're technically neutral. But there's a very, very slight offset of charge. So if I take two of them and get them close enough together, they sort of stick together. So there's a positive side to, or there's a negative side to water and a positive side to water. And when they attract to one another, they stick together. And from our personal experience, water isn't just a bunch of random molecules sitting on the ground or in a river. It's actually like a bunch of molecules that are stuck together, which gives water some of its physical properties. Now, the way that we can decide whether or not a molecule is polar is there's a few things that we have to look at: lone pairs on the central atom, the VSEPR shape, and the bond polarity, and where the dipole arrows are pointing, if they are present. So we talk about lone pairs on a central atom. We're really talking about the idea that there is a central atom, like, for example, nitrogen, and to that might have a couple of oxygens bonded to it. And so we'll have a single bond here. We'll have maybe a bunch of unshared pairs of electrons on the central atom. We're going to have a double bond here. We're going to put brackets around this because this happens to be polyatomic ion. Oops. So there's that. Now, when there's an unshared pair or a lone pair of electrons on the central atom, there's nothing to actually cancel out the large negative charge or large negative space that's created there. So one of the ways that we can try to signify that is if we try to shade this in or try to create the space that these electrons are going to move. So in a unshared pair of electrons on the central atom, they're going to kind of push out from each other as far as possible and create this negatively charged space on top of that or on that particular central atom. And as a result of that molecule itself automatically becomes polar because there's nothing to offset that unshared pair of electrons on the central atom. Then we talk about VSEPR shapes, and those are the shapes that we talked about yesterday and the day before. If by chance there is a unshared pair of electrons on the central atom, so if there's a lone pair or unshared pair of electrons on the central atom, the molecule ends up being polar because of that large negative charge. The types of shapes that would exhibit this would be bent and trigonal pyramidal. If the VSEPR shape does not have a lone pair on the central atom, then all of the remaining molecules could be nonpolar, or they could be polar depending on the electrons around the central atom and what they're doing. So examples of shapes that could be nonpolar or polar would be linear, trigonal planar, tetrahedral, trigonal bipyramidal, and octahedral. And we'll go through a bunch of that going shortly. The other thing that we should consider is that what the bond polarity and the dipole arrows are doing. So we know that dipole arrows in a molecule, they pull toward the more electronegative atom. So if I draw a dipole arrow like this here, that is awful, like this here, they're going to be pulling toward the more electronegative atom. So that means that the electrons are being pulled in one direction. If the molecule itself has dipole arrows that are in opposite directions, so something like this, and they're basically the same size, then they can cancel each other out. It's the equivalent of taking one car with two cars with the exact same engine and the exact same torque and specs and all that other stuff, tying them together and flooring it and having them drive in opposite directions. In theory, neither car should go anywhere because both cars should cancel each other out. If by chance, though, there is no dipole arrow to cancel it out, then if I take one car and I tie it to my imaginary car, for example, and I floor the first car, the imaginary car can't stop the car from going anywhere, so it continues to go. So when there's dipole arrows that don't cancel each other out, then we have a polar molecule. Now, we're going to use this information to go ahead and try to show you an example. So here we have carbon monoxide and carbon dioxide. And I'm telling you in this, in the example here that the bond is polar, but sort of to just kind of show you, we have carbon and oxygen. We know that carbon's electronegativity value is 2.5. Oxygen's electronegativity value from the periodic table is 3.5. When we subtract that out, we get a 1.0. So that gives us a polar bond in both cases. I'm also telling you that the shape is linear for both of these. And I drew dipole arrows. So on the structure so for carbon monoxide, this is going to be the slightly negative side. This will be the slightly positive side. And for the carbon dioxide, this will be the slightly negative side, and then slightly positive side in the middle. Now, the issue is that because the dipole arrows in carbon dioxide are in equal but opposite directions, they tend to cancel each other out. So this molecule is non-polar. And it's non-polar because the dipole arrows cancel each other out. On the other structure, so in the case of, and the other thing I wanted to show you is that, so if I shade where the negative parts are, and I shade where the positive parts are, it shows you that it's sort of symmetrical and it kind of sort of cancels itself out. On the other molecule, if I shade where the positive part is and I shade where the negative part is, there's nothing that really is canceling out this dipole arrow pulling in the one direction. So that's going to make this entire molecule polar. And it's polar because the dipole arrow does not cancel out. And so that's a very basic example. So now we're going to go through about 4 more examples, just kind of really try to hammer this home. So here we have water, and we kind of already talked about water already, but we have our oxygen, we have hydrogen. There's 1 oxygen times 6 valence electrons. There are 2 hydrogens times 1 valence electron. Going to add that up and get 8 valence electrons. I'm going to place my oxygen in the center. I'm going to attach my hydrogens to it. I'm going to note that I've used 2 4 electrons, so I have 4 valence electrons to still place. My hydrogens both need 2, and they have 2. So in the bond, so they don't need any more electrons. My oxygen has 4, and it needs 4 more. So I'm going to give it 1, 2, 3, 4, and so there's my structure. The next thing I'm going to do is I'm going to identify the type of bond that's present here. So I have oxygen and hydrogen. I know that oxygen, according to the periodic table, has an electronegativity value of 3.5. Hydrogen, according to the periodic table, has an electronegativity value of 2.1. When I subtract those 2 values, I get 1.4, which tells me that the bonds are polar bonds. So if the bonds are polar bonds, I need to draw a dipole arrow, and my dipole arrows will go toward the more electronegative element. So if I do that on my structure, it'll look something like this. And if I have to draw dipole arrows, I'm going to have partial charges. So the oxygen side will be slightly negative, and the hydrogen side will be slightly positive. like this. Now, the next thing that's going to happen is I'm going to re-clean this structure up so I can try to shade it a little bit. So hydrogen, oxygen, hydrogen, electrons. And now to illustrate where the negative charge is located is I have this large negative charge here and that large negative charge there. And I also have negative charge being pulled toward the oxygen, and the hydrogen, right? It's just a little bit of positive charge. Oops, a little bit of positive charge. And that little bit of positive charge basically can't counteract all of the negative charge around the central atom, or the oxygen in this case. Let's take a second to talk about the shape here. So this could be an AX2, and it'll be an E2, which we should know is bent. Now, when we talk about this molecule itself, whether the molecule is polar or nonpolar, this is going to 100% be a polar molecule. It's a polar molecule because the unshared pairs of electrons on the central atom create a large area of negative charge. So that's how we're going to describe why water is a polar molecule. Now, let's try another one. Here I have CF4. I have my one carbon. I have fluorines. My one carbon has 4 valence electrons. I have 4 fluorines. That has 7 valence electrons. And that's 32 total valence electrons. So I'm going to draw this structure. And then I'm going to do single bonds. And each bond is 2 electrons, so I had 2, 4, 6, 8. So that gives me 24 valence electrons. My carbon has 8 electrons around it because of each of the 4 bonds. Each fluorine has 2 electrons around it, so I need to add electrons. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. I need to go ahead and identify the type of bond that's present here. So we're looking at the relationship between carbon and fluorine. So I know from the periodic table that carbon has an electronegativity of 2.5 and fluorine has an electronegativity of 4.0. And when I subtract that, I get 1.5. So I know that my bonds are all polar bonds. So I'm going to draw my dipole arrow towards the more electronegative element. So that's going to look something like this. And I'm going to use partial charges to indicate that the fluorines are going to be delta negative or partially negative, and the carbons are going to be partially positive. So negative, 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 and then this is going to be slightly positive. I should do that better. So the next thing I'm going to do is I'm going to try to clean this up a little bit and do some shading. So I'm going to have fluorine, carbon, fluorine. And then I'm going to shade the areas where the electrons are being pulled towards red. So I'm going to have some fluorines that are red. and I'm going to have some carbon that is just blue like this. If I was going to identify the geometry of this molecule, it is an AX4, and there's nothing on the central, no pairs of electrons on the central atom, so it's an AX4E0. So this is going to be known as the tetrahedral structure. Now, whether or not this molecule is polar or nonpolar, there are polar bonds, but this molecule is going to be nonpolar. Note that the electrons are being pulled in towards the fluorines in equal and opposite directions. So the fluorines going to the left and to the right, the electrons are being pulled away from each other with equal and opposite force. And the fluorines going up and down are being pulled away from each other with equal and opposite force. So that makes this molecule totally nonpolar. So how we describe that is by saying that the dipole arrows cancel each other out, and if the dipole arrows cancel each other out, the molecule itself becomes nonpolar. But not every tetrahedral is nonpolar, and here's an example of how that could be the case. So again, I have carbon, I have hydrogen, and I have fluorine. I have one carbon times 4 valence electrons. I have one hydrogen times 1 valence electron. And I have 3 fluorines times 7 valence electrons. And when I add them together, 4 and 1 is 5, 20 plus 21 is 26 valence electrons. So this time I'm going to put my carbon in the middle, just like I've done before. I'm going to add my fluorines and my hydrogen. And I'm going to start with a single bond for each. 2, 4, 6, 8. So my carbon has 8 valence electrons, so that leaves me with 18 valence electrons. My hydrogen has 2 in its bond, so that doesn't need any more. So that means that my fluorines are going to need more electrons. So 2, 4, 6, 8, 10, 12, 14, 16, 18. We now need to check out bond polarity. So we're going to look at the relationship between carbon and hydrogen and carbon and fluorine. In this case, the hydrogen has an electronegativity of 2.1 according to the periodic table, and carbon has an electronegativity of 2.5 according to the periodic table. And when I subtract those, I get 0.4. So this is a non-polar bond. The carbon and the fluorines in this molecule, nothing's really changed actually. Here's a 2.5 and a 4.0. Subtract that, get 1.5. So that is a polar bond. The shape here, there's one central atom, so that's my A. There are 4 atoms bonded to it, even if they're different. So it's AX4. And then I have an E0, making this a tetrahedral molecule. I'm going to clean this structure up so I can do some shading. And we don't need to shade anything for the nonpolar bonds, but we are going to shade our fluorines, right? Because that's where the electrons are being pulled towards, and the carbon has the electrons being pulled away from them. So, we forgot to draw arrows. Holy mackerel, let's do that now. So we're going to draw arrows toward the more electronegative element. Sorry, I got carried away. Oops. And so we're going to include our partial charges. My fluorine is going to be negative. My carbon is going to be positive. So delta negative, delta negative, delta negative, delta positive. All right. Now, so the arrows pointing up and down are basically canceling each other out. But the arrow being pointed to the right towards that fluorine has nothing to cancel it out because the hydrogen-carbon bond is nonpolar, and there is no, and so the electrons are being shared equally, so they're not being pulled in any direction. So this molecule is going to be a polar molecule. It's going to be a polar molecule because the dipole arrows don't cancel each other out. So that makes this a polar molecule. All right, we have one more example I'd like to walk through real quick, and it's the Pi3 structure. So I've got phosphorus and iodine, 1 phosphorus times 5 valence electrons, 3 iodines times 7 valence electrons. Add all that up and we get 26 valence electrons. So I'm going to draw my structure with my phosphorus as my central atom. My iodines are going to be bonded to that phosphorus with single bonds. It's 2, 4, 6. 20 minus 6, is 20 valence electrons. None of the atoms have 8 valence electrons around them, so I'm going to start adding electrons. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. So now my phosphorus has 8 valence electrons, 6 in bonds and 2 in the pair. Each of my iodines has 8 valence electrons, 2 in bonds, and 6 in the electrons themselves, or dots. So now we're going to go ahead and figure out the electronegativity difference here. And in this case, we're looking at the relationship between phosphorus and iodine. And I can see that phosphorus has an electronegativity of 2.1. And iodine has an electronegativity of 2.5. So when I subtract that out, I get a 0.4, making this a non-polar bond. So if it's a non-polar bond, I don't have any arrows I have to draw. So if I clean this up to do any shading, right, we won't have a lot of shading, but we're going to have some. And so in this instance, the electrons that are on the central atom are creating that large area of negative space. To identify the shape of this molecule, okay, we have in A, X3, E1, which makes it trigonal, pyramidal. And this molecule ends up being polar, though, even though it has nonpolar bonds. And it's polar because the unshared pair of electrons the unshared pair of electrons on the central atom create an area of negative charge. And we're going to say a large area. Get rid of that. Okay. A large area of negative charge. And so there you have it. We've gone through 4 or 5 examples about how to use bond polarity and the shape of the molecule to help you identify whether or not the molecule is polar or not. If you have any questions, make sure that you touch base with your teacher. Otherwise, good luck with this concept.